Okay, so we all know that pushing a heavy box is way harder than pushing a light one. Simple, right? That's mass. But what happens if you try to spin that box instead of pushing it? Well, it turns out there's this whole other kind of heaviness that comes into play, a resistance to being spun. And that, my friends, is called the moment of inertia.
You can almost think of it as an object's rotational stubbornness. So while mass just tells you how much stuff an object is made of, the moment of inertia is all about how that stuff is arranged. And that arrangement is what makes it either super easy or incredibly difficult to get it to spin.
So, we have this idea of rotational stubbornness, but what do physicists actually call this? Well, they call it rotational inertia, and it is the key to understanding everything from a spinning figure skater to why a giant ship doesn't just tip over in the ocean.
And here's the core idea, which is so powerful. Moment of inertia, which we usually just represent with the letter I, is nothing more than a measure of an object's unwillingness to start spinning or to stop spinning once it's already going. Just like a giant boulder is tough to get rolling, an object with a high moment of inertia is a real challenge to get rotating.
You know, at its heart, the calculation for just a single particle is beautifully simple. It's the mass, m, times its distance from the center of rotation, r. But, and this is the important part, that distance is squared. And that r squared piece of the puzzle, that's the secret sauce. It tells us that distance from the center doesn't just matter a little bit, it matters a whole lot.
But of course, the world isn't made of tiny single points of mass, right? We're surrounded by real objects with all kinds of complex shapes. And it turns out that the shape of an object is absolutely critical to how it spins.
So, let's ask a kind of strange question. Can an object be rotationally lazy? I mean, if you have two objects that weigh the exact same amount, could one be harder to spin than the other? The answer is absolutely. And the secret isn't how much mass they have, but where that mass is hanging out.
So let's take a look at these three shapes. Now they all have the exact same mass, m, and the same radius, r. But look at the difference. The thin ring, with all of its mass pushed way out to the edge, is the hardest to spin. It has the highest moment of inertia. But watch what happens when we take that same mass and arrange it into a solid disk. Suddenly, it's way easier to spin. Its inertia is cut in half. And if we squish all that mass into a solid sphere, concentrating it toward the center, it becomes the easiest of all. It's the same mass, but a completely different story when you try to spin it. So here it is, the big takeaway. It's not just about how much stuff you have, it's about where you put it. Pushing mass farther away from the axis of rotation dramatically, and I mean dramatically, increases an object's resistance to spin. That is the fundamental principle of moment of inertia. Right there. Okay, spinning things through their center is one thing. But what if you want to spin an object around its edge? You know, like a door swinging on its hinges. Well, physics has this incredibly clever shortcut for figuring that out. It's called the parallel axis theorem. And trust me, it's way more elegant than it looks. It simply says that the new moment of inertia, I, is just the inertia through the center of mass, plus one extra little term, the total mass, m, times the squared distance, d, that you shifted the axis. And what this really tells us is something profound. An object is always easiest to spin around its center of mass. Any other point is going to be harder. And actually, using this theorem is as easy as 1, 2, 3. First, you just find the standard moment of inertia through the center, which we already have formulas for. Second, you measure how far you're moving the axis of rotation. And third, you just plug those numbers into the formula and add them up. It's a super powerful tool that lets you solve for basically any axis you can think of. So why does any of this actually matter outside of a physics class? Well, because moment of inertia is the hidden principle that makes so many things in our engineered world actually work.
Have you ever wondered how a car engine runs so smoothly when it's basically just a series of controlled explosions happening over and over? Part of the magic is something called the flywheel. It's designed to be heavy, with most of its mass on the outer edge, which gives it a huge moment of inertia. This means it fights against any change in speed, storing rotational energy and smoothing out those jerky power strokes into a steady, reliable hum. Or, get this, it's kind of mind-bending. For the same amount of steel, a hollow drive shaft is actually stronger and can handle more torque than a solid one. How is that even possible? Yep, it's all about moment of inertia. By pushing the mass away from the center, the hollow shaft has a higher resistance to twisting. It's a brilliant piece of engineering that gets you more strength out of less material. In this principle, it scales up, way up. The stability of a massive ship out in a stormy sea literally comes down to moment of inertia. Engineers meticulously calculate and distribute the ship's mass to maximize its resistance to rolling and pitching. And getting that calculation right, that's the difference between a safe voyage and a total disaster.
So there you have it. From a simple spinning ball to the design of a massive ship, you now see the hidden physics of spin. So take a look at the world around you. What could be made better, or faster, or more stable, just by cleverly rearranging its mass? The moment you start thinking about moment of inertia, you'll start seeing the possibilities absolutely everywhere.